This time we'll be talking about text classification and sequence labeling, and about half of this class or half of the lecture portion of the class will be kind of more or less review for some of the very basic things regarding building neural network models for natural language processing tasks in general. If you participated in 11.7.11 or a similar class, this will mostly be review or stuff that you know already. But I think it's important because there are other people who are coming from other backgrounds who haven't done that before, so it'd be good to have the basics before you dive into the code. In addition to that, I'm going to be talking about kind of text classification and sequence labeling from a more like multilingual perspective. So giving some pointers to data sets and tasks and other things like that. So hopefully that'll be useful even if you've taken another class that's covered that before. And actually, I'm going to mute everyone. So feel free to ask questions at any time. You can either raise your hand or ask via text or unmute if you're allowed to do that. Great. So then after we finish this, we'll have a walk through the assignment, including a look at what is required for doing assignment 1 and the code, et cetera, et cetera. I think potentially the assignment 1 description on the website is like a little bit old, but we'll be updating that very shortly. Okay, getting started, text classification and sequence labeling. So text classification and sequence labeling are both very broad, like I like to call these task categories. They're not tasks in and of themselves, but they're categories of tasks that all look very similar and thus can be solved in similar ways. So text classification, given an input text X, predict an output categorical label Y. And this can be all kinds of different things, like topic classification, where we take I like peaches and pears, and that gives us the topic food. And I like peaches and herb, and that gives you the topic music, because peaches and herb is a old band, basically. We have language identification, which is a particularly important task in multilingual learning. And basically, this is taking in language and outputting, taking in text and outputting the language that it's written in. So, obviously the first is English and the second one is Japanese here. This becomes very interesting and difficult, as I'll be elaborating later in the lecture portion. Another example that's very widely known is sentiment analysis, and this can be done at the sentence level, the document level, or you can even do sentiment analysis with respect to individual entities or things like that. But from a text classification point of view, it would be like sentences or documents. So if we have I like peaches and pears, that'd be positive. I hate peaches and pears, that'd be negative, obviously. And there's many other tasks that fall into this. Sequence labeling, on the other hand, is given an input text X, predict an output label sequence Y, usually of equal length. So this can be formulated as taking in a sequence of words and outputting one tag for each sequence of words. So we have part of speech tagging is one example of this. So we take in words and output parts of speech. Another one is lemmatization. So what this is doing is it's basically taking in words and outputting their base form. This is used sometimes in English, but it's actually particularly useful or important in languages that have richer morphology than English, because essentially, if they have lots and lots of conjugation or other things like this, the words themselves can become very sparse. So identifying the underlying base form helps you understand like what the word is referring to better. Another variety is morphological tagging. In morphological tagging, we're going to be talking about morphology in about 2 classes, but basically it's predicting various features of the word based on, like, for example, here we have he saw becomes the past tense and a finite verb form. It's a number and the type is a cardinal number. This is plural. For example. So this can become more complicated with more languages that have more complicated morphology also. And there's other ones as well. There's also span labeling tasks, and sometimes these span labeling tasks are treated as sequence labeling tasks, but they're actually a little bit different. And basically the idea is given an input text X, predict output spans and labels Y. And these include things like named entity recognition, where you want to identify the spans and labels on the spans for named entities like person, people, or things. So here we have Graham Neubig as a person and Carnegie Mellon University as an organization. Another example is something called syntactic chunking or shallow syntactic parsing, where basically you want to split up the sentence into like noun phrases and verb phrases like this. That's another example. And there's also semantic role labeling, where semantic role labeling basically identifies spans and tries to identify like, this is an actor, this is a predicate, and this is a location. So what role each of these arguments is playing with respect to the predicate. But as you can see, all of these basically have to do with like identifying spans and labeling them in some way. So span labeling can also be treated as a sequence labeling task. So you predict the beginning, in, and out tags, BIO tags for each word in the span. So if we take our span labeling task like this, where we want to identify a person or organization, we convert this into a thing where we basically have one task or one tag for each word. So we have beginning of person, inside of person, out, 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 which means no span is identified. Beginning organization, in organization, in organization, like this. So the good news is then, if you want to do this span identification task, you can just solve it with a sequence labeling model. So sequence labeling is nice in that way. There might be better ways to handle span identification, but this is one way to do it. So another task that is slightly different, but also can be handled as sequence labeling is text segmentation. So given an input text X, split it into segmented text Y. So a very common example of this in many languages is tokenization, where you want to take something like a well-conceived thought exercise that has like lots of punctuation and intervening hyphens and stuff like this, and split it up into things that look a little bit more like just kind of natural word boundaries, like this, adding spaces between each of the punctuation, etc. Another variety of this, which is necessary for some languages, not so many languages in the world, but some languages, is word segmentation. And this is an example from Japanese, because Japanese is written with no spaces between words. So you can't just split on white space using your Python like split function. You have to actually find the locations of the word boundaries. And this is a non-trivial task. This is one segmentation that you could have here. This is the kind of like quote unquote correct segmentation. But you could also make a mistake and segment like this. And this phrase itself, if you split it this way, means foreign people voting rights or like suffrage for non-citizens. Whereas this means the foreign carrot government. So basically, if you split the correct way, you get one meaning. If you split the wrong way, you get another meaning. And this can, mess up information retrieval systems, any translation systems, anything that you would think of. And then there's also morphological segmentation, which again, we're going to talk about a bit more, which is, for example, we might have something that looks a little bit like this, which can be split into different ways. I believe this is Turkish, I think. Someone can correct me if I'm wrong here. I actually forgot where I got the example, but I believe it's Turkish. So then we have dog and plural, or dog paddle and a tense. So basically, whether you split it one way or the other also affects whether this is like a plural noun or a verb. And thank you for confirming that this is indeed Turkish. So this is another issue that you could have. Cool. Are there any questions about this so far? Oh, is the word segmentation solved with additional context in Japanese? Yeah, that's a really good question. And morphological analysis also is similar, having context. So basically, yes, having context is very important because both of these are reasonable morphological segmentations in different contexts. They're both things that could happen. Sure, this might be a lot more frequent, but there certainly are examples where this would occur. It's also the case in Japanese, although that's a little bit more rare. Like one example is that I can put into Zoom. Chat. This means if you split off the first character, that means American nuclear reactor. If you split off the second character, it means a train that's departing from Maihara, which is a place in Japan. And so depending on whether you're in a newspaper article or a train schedule, either of those would be correct. So it's, yeah, it is based on context. Then I had another question explaining the distinction between B and I here. So B basically is the first tag in a sequence in a span. So it would be applied to the first word in the span. I would be applied to every subsequent word in the span. So if you had a single word span, it would just have a B, but if you have a multi-word span, it will be B, I, until the span finishes. And having these two different tags is necessary to distinguish cases where you have two spans in a row. So if you have like person and then another person later. How do we constrain the model so that B is predicted before I for a particular entity? That's another really good question. So if you, maybe I'll talk about how we actually do this prediction first and then get back to that question later. Great. Okay, so I'd like to talk a little bit about modeling for sequence labeling and classification. So the first question is, how do we make predictions? So given an input X, input text X, extract features H, and predict labels Y. And the way this works is basically we have text classification and sequence labeling. So we have like, I like peaches. We have some sort of feature extractor that extracts a whole bunch of features from the whole sequence into like a single vector here. And then given that single vector, we make a prediction. We have, for sequence labeling, we have a feature extractor that extracts one feature or one vector of features for each word in the input, and then we make a prediction from this, like that. And so either way, we need a feature extractor. It's just a matter of whether we are extracting a single vector of features for the whole sequence or one vector for each word. So a very simple feature extractor that we might use for text classification, for example, is bag of words, where what we do is we look up a single feature for each of the words, and then we add them together to get a vector representing the number of times a particular word occurred in the sentence. And then we feed this into a predictor. Maybe we have a matrix multiply that turns this into label values, and then we use this to calculate label probabilities. So just to clarify, when I say bag of words, we have a one hot vector, which means a single value in this vector here is 1, and all of the other values are 0. So this is essentially a vector that represents the identity of the word and nothing else. So as our simple predictor, we can have something like a linear transform and a softmax function. So what that looks like is we take the extracted features, we multiply them by a weight matrix. We add a bias here, which tells you essentially how likely each of the labels is a priori. And then the softmax converts arbitrary scores into probabilities. So we exponentiate the score at each of the elements in the resulting vector, divided by a normalizer to make sure that all of them add up to 1. Oops. Add up to 1, and then that gives us a probability of our final output. So it might look a little bit like this. After the linear transform and bias addition, we might have a score vector that looks like this, and we turn it into a probability vector. So I think this should be pretty familiar to a lot of people. No questions about this? Any questions? If not, I have a little bit of a quiz. So like we talked about text classification. Sorry, every time I touch my mouse, it moves my my slides. It's a little bit annoying, but so we talked about text classification where we extract features for the whole sequence. And then we use that to predict the label probabilities for the whole sequence by adding all of these together. What do you think of a bag of words of a similar feature extractor used for sequence labeling? Does that make any sense whatsoever? So we extract one vector using this kind of bag of words lookup function and then make predictions based on this vector. Would that do anything? Would that be a reasonable way of solving this problem?
Maybe not so reasonable because it's neglecting the word order.
Yeah, maybe not so reasonable because it's neglecting the word order. Yeah, that's a pretty good idea. But it's actually maybe not that bad, right? What it would end up doing is it would basically look up I, and then it would make a prediction of what part of speech tag I would be based on what the most frequent part of speech tag for I is. And it would make the prediction of like, and it would make the prediction of the most frequent thing for likes. So yeah, it's a frequency-based model. It would be looking up the majority class for each word. And actually for part of speech tagging in English, and even more so for other languages, this actually isn't that bad at part of speech tagging. It gets like high 80s accuracy just because there's relatively little, like peaches is always a plural noun. I can't think of any case where it wouldn't be a plural noun. So even that would be, a moderately okay feature extractor both for classification and sequence labeling. However, it does neglect the word order. So if you want to do like even better than just majority class, you'd have to come up with some other way. So another issue Language is not just a bag of words for classification or labeling. So to have some examples, we have I don't love pears. There's nothing I don't love about pears. If you just look at the words in the sentence, like love is the positive word, and then you have a negation, but negation in itself is not, very indicative of positive or negative sentiment. So both of these would be relatively hard to tackle with a bag of words model. So what we want to do is we want to come up with a better featurizer to better pull out features for our sequences or for each word in our sequences. So one example of a better featurizer might be a bag of n-grams model. So basically, instead of looking up each word, we would look up each n-gram. So here, for example, then don't love would also become a feature in our model. And if don't love is a feature in our model, that's kind of like a negative feature, right? It would maybe overpower the love feature and move that more negative. You could also come up with syntax-based features like subject-object pairs, or neural networks, like recurrent neural networks, convolutional neural networks, self-attention. And so until 2015 or so, it was very common to use these kind of handcrafted features, or at least handcrafted feature templates, and throw them into a support vector machine model or something like this to do text classification. Now it's much more common to use neural networks, and they also have some really nice properties like allowing transfer across languages, which is a very big part of this class. So we're going to mainly be focusing on these models in this class. This time I'll talk about recurrent neural networks just because they're conceptually easy, but we're also going to be talking about things like self-attention later. So a neural network, which a lot of people know, is basically a computation graph that is parameterized in a certain way in order to allow it to make predictions. The name neural networks comes from neurons in the brain, where basically, they take in information across synapses, and then they fire and they give output over the output synapses. But the current conception of how we use them, it's basically a mathematical object that allows us to calculate something, take in an input, generate an output. And in particular, in this case, it's going to be our featurizer and our predictor. So it's going to take in an input, output some features for each word or each class, or it's going to take in an input and output a score for each class. So if we define an expression, the way we represent it as a computation graph is through nodes and edges between the nodes. And so here we have a single variable, maybe a vector, and that's represented as a single node. The node can be like a scalar value, a vector value, matrix value, tensor value. And we can also have operations over all of these values. So like, let's say we transpose the vector, that operation would be demonstrated as an edge to another node that implements the transpose. So an edge represents a function argument, and a node with an incoming edge is a function of that edge's tail node. And a node knows how to compute its value and the value of its derivative with respect to each argument. And then functions can be nullary, like input values here, or unary or binary. So here's something representing a matrix multiply. So basically now we have X transpose times A here. And these are directed in acyclic graphs that allow us to calculate more and more complicated expressions. So they allow us to do things like calculate features, make predictions, etc. And we can also name individual parts of the graph. And this allows us to calculate values that we would like to be calculating, like the score of the probability of prediction, for example. And so some algorithms are graph construction and forward propagation that allow us to calculate values. So forward propagation, basically, we start out with the input values to the graph, and we gradually move through the graph to calculate the final result here. And we also have back propagation. And back propagation, basically what it does is it processes examples in reverse topological order, calculating the derivatives of the parameters with respect to the final value. And this is usually the loss function, the value we want to minimize. So in many cases, this is the negative log likelihood of the predictions over the true values. And by minimizing this negative log likelihood, that allows us to maximize the probability of getting the correct answer. And then we take the derivatives calculated through back propagation to update the parameters of the model. So back propagation basically works like this. We start from the end of the graph and gradually move back until we back propagate into parameters. So let's say A was a parameter, B was a parameter, and C was a parameter. We would back propagate into these values. And once we have the derivatives that we calculate through this process of back propagation, we can use them to update the parameters to kind of improve the likelihood of getting the correct answer. So this is a kind of 5-minute intro to neural networks. If you're not very familiar with them, there's lots of good tutorials online. In particular, we're going to be using a neural network framework, PyTorch, for examples in this class that I think a lot of people are familiar with already. And our first assignment this time is aimed to kind of have the dual purpose of allowing you to get familiar with building models in PyTorch and stuff like this, and to also learn more about kind of the interesting difficulties that you have to deal with when you apply these multilingually. So if you've already taken a class or already used neural networks pretty widely in your work, then all of this will be old to you, and you'll more or less know this already. If you haven't, then definitely take advantage of the TA office hours. Look at the examples, ask lots of questions. We can forward you some tutorials online to help you out as well. So this will be your chance to catch up before we get into the more involved assignments that happen later on. So yeah, actually, maybe I'll skip that part. So to give an example of a type of neural network that can be used for featurizing a text classifier or a sequence labeler, we are going to talk briefly about recurrent neural networks. And recurrent neural networks are models that allow us to do precisely what was mentioned before as being the issue with a bag of words model, which is handling either short or long distance dependencies in language, handling word order, handling other things like this. And so in language, there's many dependencies that span across whole sentences. So for example, agreement is one example. There's not a whole lot of agreement in English. Like, for example, there's gender agreement, and there's a plural, there's like number agreement between subjects and verbs. So here we can see he and himself need to agree, she and herself need to agree. Also, he does needs to agree here. So if this were I, it would be I do, he does. So that's an example. Also, word order in general. We talked about that last class. So we need to have some sort of model that's able to handle these things. These are syntactic characteristics that we need to be able to handle. And there's also semantic characteristics. So for example, we need to have semantic congruency between rain and queen and rain and clouds here. They're just things that make sense semantically and don't make sense semantically based on our knowledge of the world. And we also need to handle these as well. So recurrent neural networks basically are one of the tools that we could use to encode sequences, either to get representations for each word or representations for other words. So basically what recurrent neural networks do is they look up the context or the input at the current time step, do a transformation of this into features, and then they feed in the features from the previous time step to the next time step. So to give an example, if we have I, we would feed it through an RNN and get the next vector here. Like, we would feed this through another RNN function. We would calculate a vector corresponding to like. This is a parameter of the model. And then we feed in the result of running I through the RNN to get the, and this input here to get the representation for I like. And then we have these, and we calculate the representation of these. I like these, and then we have pairs, and we calculate the representation of I like these pairs. And basically, this is a recursive function. So each time you're using the result of the previous function to calculate the result of the next function. So when we represent a sentence for text classification, basically it would look a bit like this. So we would take the last vector in the sequence to make a prediction. And that would be useful for things like text classification, condition generation, retrieval. We'll be talking about the latter two later in the class, but text classification is the one we're talking about this time. And it can also be used to represent words. So if we wanted to predict a part of speech label for I and like and these and pairs, we could use the immediate output after inputting that word to try to make that prediction as well. And this would allow us to do things like pull in context from the left side to make this part of speech prediction. For things like sequence labeling, language modeling, calculating representations for parsing, etc. So the way we train the RNNs is like, let's say we're training one for sequence labeling. We have the predictions here. From these, we could calculate a negative log likelihood or a loss function, something like this. We have the label. We use the true label of the output to calculate a loss function. And we add them together to get the sequence level total loss. So this is one big computation graph for the whole sentence. And then we take the total loss and we do backpropagation from this total loss into the whole, into the representations for the whole sentence. So the parameters of the model are all tied across time. The derivatives are aggregated across all time steps. And this gives us something called backpropagation through time. So you can backpropagate through the whole sentence and basically optimize the probability of making the correct predictions for the whole sentence. So what did I mean by parameter tying? Basically, the parameters are shared between this RNN function over the entire sentence. And because of this, this allows you to apply this to sentences of arbitrary length. So if you have a sentence of length 50 or a sentence of length 20 or something like this, then this would essentially allow you to represent all of them within the same recurrent neural network by just applying this RNN function 50 times or 20 times or 3 times for a 3-word sentence. And when doing representation for things like sequence labeling, it's very common to use bidirectional RNNs. And what I mean by this is basically you take the left side and you run a recurrent neural network that steps from time step 0 to time step 1 to 2 to 3 to 4. from left to right. And then you have another recurrent neural network that steps from right to left in this way, and aggregates information from both of the directions, concatenates that together, and makes a prediction. And the reason why this is useful is you never know whether the context to disambiguate a particular word would be available on the left side or the right side. So this allows you to pull in information from both sides. Okay, so that's basically the overview of a simple method for doing calculation of either representations for the whole sentence. So for example, if we're representing the whole sentence, we might take this vector, we might concatenate the right side of the left RNN and the left side of the right side of the forward RNN and the left side of the backward RNN. Or if we want to represent individual words, we might concatenate together the things at each time step to make predictions. So this would allow us to do text classification or sequence labeling. Okay, are there any questions about this before I jump into the multilingual part? Okay, I guess not. So we can jump into the multilingual thing that is part of the name of the class, of course. So I'm going to be talking about some text classification and sequence labeling tasks. Most of these are tasks that are applicable to any language, so they're explored quite widely on English as well. But some of them are inherently multilingual. So for example, language identification is one that's inherently multilingual. So language identification, as I mentioned before, is the task of identifying the language that a particular text comes in. And this is really important for a very broad number of reasons. The first reason might be if you want to create like let's say you want to show people content in only a language that they speak. So, people, when they're doing search online, they'll probably more appreciate results in the language they speak than in another language. Another example could be for creating data sets for something like machine translation or language modeling or something like this, where you only want data in a particular language, and other things like this. So actually, one of the largest language identification corpora was created by Ralph Brown here at LTI. It's a benchmark on 1,152 languages from a variety of free sources. So this is kind of a widely known data set here. If you want off-the-shelf tools for doing language identification, one example of a relatively easy one to use is langid.py. So you can just download this, use it for 90+ languages. Another example is there's the Chrome language identifier from the Chrome browser. I actually don't have a link here, but that's also pretty widely used by people if you want an off-the-shelf method that you can use. There's also a nice survey. It's a little bit old by now, but automatic language identification in texts, which I can recommend. You can take a look at if you're interested in this. And I'm missing a slide that I thought I had added here. Weird. Okay, so I will just discuss. I'll just discuss this paper. So this is a recent paper from 2020 by people at Google working on kind of low resource languages. It's quite interesting. It's called Language ID in the Wild, Unexpected Challenges on the Path to a 1,000 Language Web Text Corpus. And this is not the only paper that has pointed out this problem that language identification doesn't work well. But they have some very interesting insights, and they also have a very nice kind of example of the issues that you encounter when trying to do language identification on web text. And so here are some mined sentences from the web that were supposedly in one language, according to Google's text like language identification model. So like a whole bunch of people raising their hand in emojis got classified as Manipuri. This was in Twi, which is why you lion, why you always lion, written in kind of like strange characters. A misrendered PDF was Farhadi. The non-Unicode font, I'm not sure what this was. Yeah, it's a non-Unicode font, I guess, was written in this way. Here, this was as Balinese, it was just like boilerplate. This was also English, but it was written in like the Cherokee script for stylization. If you just wrote meow, that became kular. So you can see basically here, when people write in like slightly non-standard language, it gets identified as other things. Like even this is like clearly standard English, but there were hints of words that often occur in Oromos. So it got recognized as Oromos. So this kind of just demonstrates how difficult this task is when you start applying it to web text. And I actually had a similar experience when I was trying to do Twitter. There was a certain like face, like not emoji, but like the faces written with regular characters. It was written in Kannada characters. And so many things were recognized as Kannada just because they use that like popular face. So there are lots of large corpora. Like while I'm at it here, I can also introduce the Oscar corpus. This is a very large corpus, huge and multilingual, obtained by language classification and filtering of the Common Crawl corpus. It's gotten a bit better since they first released it in terms of the noisiness, but when it was first released, it was like extremely noisy just because language ID didn't work so well. So this is actually like a really big problem that you need to be aware of if you're starting out. Are there any questions about language ID before I move on to the next one? Okay. So also kind of standard text classification, like as I said, text classifications were like a class of tasks than a task in itself. Here are some representative ones that people have used. These are mostly used for benchmarking multilingual models as opposed to like actually building anything useful. But still, you know, sometimes you want to know how good your multilingual representations are, so they could be good test beds. One example is the MLDoc corpus, which is a corpus of multilingual document classification. There's also the PAUSE-X corpus. This is a paraphrase detection between languages. It's sentence pair classification where you feed in two sentences. Also cross-lingual natural language inference. So this is textual entailment prediction or natural language inference, which is also a sentence pair classification task. There's also cross-lingual sentiment classification in Chinese and English. So this could be used for sentiment. Another thing is part of speech and morphological tagging. I'm not going to go into a whole lot about this because I know it's going to be covered more when we talk about like words, parts of speech, and morphology. But basically, there's the universal dependencies tree bank. And the universal dependencies tree bank, basically, it contains syntactic parses, like dependency parses, but it also contains parts of speech, and morphological features for 90 languages. And it has a standardized universal part of speech set and universal morphology tag set to make things consistent across the languages. So this is one of the highest quality, like multilingual corpora that I'm aware of. It's, you know, well controlled, well conceived. And there are some pre-trained models that can use, that can do like syntactic analysis on many languages trained on these data sets, like Unify and Stanza, if you're interested in doing multilingual like syntactic analysis. So named entity recognition, this is going to be what we're going to be doing for the assignment. And there's different types of named entity recognition data sets. There's a gold standard data set from Connell 2002, 2003 on language independent named entity recognition. This is in English, German, Spanish, and Dutch with human annotated data. I actually forgot to add one that I just remembered now that just came out. I helped out with this a little bit. But it's a named entity recognition data set for African languages called Masakan, and this is nice because it's also manually labeled, but it's in African languages that have like a lot fewer resources than English, German, Spanish, and Dutch. So it gives kind of a better idea of like, you know, how well we'll be doing on lower resource languages. There's also this WikiAN dataset for entity recognition and linking in 282 languages. This was extracted from Wikipedia using interpage links. So in Wikipedia, of course, if we go to Carnegie Mellon University on Wikipedia, there are many links. So there's no link here, but here's Pittsburgh, Pennsylvania, the Mellon Institute of Industrial Research, Andrew Carnegie. So all of these links link to other pages. And then if you look up the type of the page, according to some annotations that come on Wikipedia, you can tell that Pittsburgh is a city, Mellon Institute of Industrial Research is an organization, and Andrew Carnegie is a person. And then, of course, you know, this is available in lots of languages. So we can go to Chinese and find the Chinese equivalent of Andrew Carnegie or the Chinese equivalent of Pittsburgh and do the same thing. So basically, this data creates that in many different languages. There's also several composite benchmarks for multilingual learning. So they aggregate many different sequence labeling or classification tasks for testing multilingual models. One popular one is Extreme. It's a massively multilingual benchmark for 10 different tasks, 40 different languages. Another one that came out at a similar time is Exclu with 11 tasks over 19 languages. So there's also a new version of Extreme called Extreme R that just came out. I've been a little bit involved in both of these. And Extreme R is, they swapped out some easy tasks, added some harder tasks, and added better analysis. So you might also consider looking at that. For your class project, I would warn you that these benchmarks are very popular, and there's people with like lots of compute that are competing on these benchmarks. So you might not, it might be a bit of a challenge to keep up with the state of the art there, but I think you could work on individual tasks and still do a very good job, like some of the tasks where kind of generic models are not working as well. So you could definitely take a look to get inspiration for ideas. Okay, great. So that's all I have. Are there any questions before we move on to the like discussion period, which in this case, we're not doing discussion, we're having a presentation on the assignment, but any question about data sets or tasks or? Oh, sorry, the homework was on NER. I said it'd be on NER, but it's on part of speech tagging. I apologize. Cool. Yeah, but we'll have the description of the task for assignment 1. Before I go into that, I'd just like to point out that starting next time, we will indeed be having discussion and reading assignments. So the reading assignment for next time is this modeling language variation in universals, a survey on typological linguistics for natural language processing. The reading is actually, it's only required or suggested that you do sections 1 through 3. But the whole survey is good. So if you don't mind reading 30 pages or so, it would be worth taking a look at that as well. So required is 1 through 3. And then based on what you learned in that reading, you can try to think of what are some unique typological features of a language that you know regarding phonology, morphology, syntax, semantics, pragmatics. You don't need to cover all of them, but you can cover like 1 or 2 of these, and we'll have a discussion where everybody will share what they came up with. Cool. And today is assignment 1 introduction. Tia or VJ or who's going to be presenting this time? Cool. Are you speaking? If you're speaking, you're on mute. Do I need to unmute you?
I don't think he's on mute.
Okay, there we go. Now we can hear you.
Tigray, I think you are talking, right?
Can you hear me now?
Yep.
Yes.
Oh, great. Okay. So, okay. Yeah. Hi. Hi, I'm Tigray, and Tia is going to give some introduction. Yeah.
Right. So this first assignment is to give you a practical introduction to multilingual parts of speech tagging. And I think briefly it was mentioned. So part of speech is just lexical categories or word classes or tags. So in the example sentence, he saw 2 birds. We assign the part of speech, pronoun to he, verb to saw, and so on. So you'll get a data set of sentences in different languages, and you want to output the POS tags for each of the words in the sentence. Yeah, so as mentioned previously, aside from giving you guys a practical introduction to multilingual pause tagging, we want to give you sort of like an experimental approach to multilingual problems, such as investigating the challenges to languages which are low resource, meaning that there's a limited availability of labeled data. And of course, just be familiarized with deep learning frameworks, AWS, and multilingual data sets. So to do this assignment, you would need a machine with a GPU. So you can use AWS or you can use your own computer if you have a GPU, and you'll have to install some Python packages for this assignment. So the tricky part here, I guess, would be like the AWS setup. So shortly, I'll be posting instructions on Piazza on how to request AWS credit. And I think the assignment will have further instructions on how to set it up. And all students should have an AWS account using your Android email and just follow the instructions on how to set it up. We tried doing the assignment without a GPU, but it's strongly recommended because I think the next assignments are not really doable without a GPU. And I trained it on a very old MacBook Air, and it took me around 3 to 4 hours to complete the training. And you need to retrain it, when you're changing the parameters and so on. So yeah, do it with a GPU. And I think one more thing to take note is that make sure that you stop the AWS instance when you're not doing it, because you will be continuously billed. So I think the AWS setup should be fairly straightforward. I'm not sure myself. Tingri has done it before without instructions. but the instructors and the TAs of the Intro to Deep Learning course have provided a very comprehensive AWS fundamentals playlist. So it will be linked in the assignment handout page as well. And you can follow the steps in case you have any difficulties.
Yeah, so for this assignment, we are going to give you a zip file, and this zip file will contain all the code and the data that is to use for this assignment. And we will post the link later on Piazza. So in the zip file, you can find the training data. It is the training data for 6 languages. And the right-hand side is an example what the format look like for this training data. So this is an example of one sentence. So you can see there are the words and the PLS text of that word separated by some new lines, and each line contains a word and its text separated by a tab. But actually, you don't have to worry too much about this format because our code will handle this for you. And in this homework, we are going to use this simple baseline model, a BiRNN model. It is a model with an embedding layer and also a bidirectional LSTM layer. And so the input of this model will be a sequence of words, and the output will be a sequence of POS tags. So let's work through the files in the zip file. So the first file is the config.json file. It is the file that contains the hyperparameters that will be used to train the model. You may have to change this file in order to write a report when you are doing some analysis. And this udpos.py file is the place where we implement how to read a data set. But actually, I don't think you will have to modify this, so I won't go into detail here. And this model.py file is the place where we implement this bidirectional LSTM model. And if you are familiar with PyTorch, then you can see it's a very simple model. It just simply apply an embedding layer, and then LSTM layer, and then finally predict the tags using a fully connected layer. Yeah, but if you want to make a stronger model, then you may have to modify this file. And most of the complex jobs are done in this main.py file. It handles the loading of the data, and it also do some preprocess and do the thing that have sample into batch, and also the part that trains the model. So let's go through its content. So the first thing it does is that it load the data set with the function we define, and then it build a vocabulary for the input text and also the output POS text. The reason that we want to build this vocabulary is that in modern deep learning framework, we are when we are using a embedding layer, what the embedding layer does is that it map the index of some words into some batches. So that's to say, before we can use this embedding layer, we need to first build a mapping that can assign each word with an index. So we have to iterate through the training data to see what the words that occurs in the training data. And for similar reason, we have to iterate through the data set to see all the possible POS tags in this data. So these are the purpose of these lines. And once we have the mapping that map the tokens to the indices and the mapping that map the POS tag to the index, we can define these two functions that convert the training data into indices. And with these two functions, we can define this collect batch function. The purpose of this function is that it packs a bunch of text label pairs into a single batch, and then this batch will be used to train a model. So yeah, so what this function does is that it first convert the words inside the samples to a tensor by coding the function we defined above. And it also convert the tag into indices by coding the function. And then the most important thing it does is that it pairs those sequence of tokens into the send length. So those tensors can be stacked into a single tensor, and that single tensor can be later used to train the model. And once we have this collect batch function, we can define a data loader. A data loader is an iterator. We can get some batches from it by iterate through this data loader. So here we define 3 data loaders for the training set, the validation set, and the testing set respectively. And then we can use the data loader to train our model. The way we train our model is that we repeat this process for a certain number of times defined in this hyperparameter mass epoch. And the process is that it first train the model by using the training data, and then evaluate the model using the validation set. And if after this epoch, the model get a better validation loss, then this script will save the model to some place. So at the end of this training process, you will have the model that has the minimum validation loss. As for what this train function does, it is also very simple. It just iterates through the data loader, the train data loader, and then make prediction over the text, and then compute a loss by comparing its prediction and the ground truth tags, and then use this loss to do backward propagation, and then code the atomizer to update the parameters in the model. Yeah, so it's basically what our codes do.
So what you need to submit for this assignment is code and a write-up. So part of the, how to obtain points for this assignment is you need to run the code, you need to make modifications to the model and so on. But it's also equally important to give a detailed explanation on the results that you see or what you do and why do you think your changes have made an effect on the results. And you can submit this on campus. And I think this is the part that everyone really wants to see is how do I get a good grade in this assignment? So there's a lot of ways. There's a lot of tiers as well. So if you just want to you can get a B by just running the code on the existing English model and just running the model on the test set, you'll get a B. But if you train the model on the different multilingual data sets and you evaluate them using their respective test sets, you'll get a B+. To get anywhere of an A, you need to write a report with detailed analysis. So there's a lot of ways you can comment on the results. You can see how the performance varies across the different languages. You can also see, which tags are most often misplaced for other tags. So, if are pronouns and nouns more easily mistaken for each other and so on. So that's what we want to see. And if you have a report, detailing all these explanations, you'll probably get an A-. To get an A or above, you will need to create a non-trivial extension to improve the existing scores. And there's really a lot of ways you can do this. You can add like CNN input layer to capture character level features. You can use pre-trained embeddings and so on. So there's really, it's kind of like an experiment that you need to run on your own, and we're excited to see your results. So if you find any problems understanding the assignment or setting up AWS, downloading the packages and so on, please feel free to drop in our office hours. Mine is actually at 3 p.m. today, right after this class. So I'd be happy to answer all the questions that you have, or if you require additional help. And you feel free to contact us through our emails, or you can post a question on Piazza.